This next topic really started with the question, what fuzz was used in The Spirit in the Sky? And the answer I found was a heck of a lot more than just putting a name on a schematic, right? Let's take a closer look. Here's the rabbit hole that I found myself going into, comparing all of the circuits and the schematics that I found from the 1960s. 8 topologies started to emerge. Okay, now what does that mean? It means I kept finding circuits that looked different. They had different component values and such, but they were fundamentally doing the exact same thing. So I started to sort them into different groups. For example, 11 of them were all examples and variations of the Maestro FZ-1 fuzz tone circuit. Another 20 were all different brands of a Fuzz Face. Another 12 were iterations on the Sola Sound tone bender. Then we had 6 different Octavias. We had 5 different Fuzzrite circuits. And then we had some diode clipping circuits, which were almost exclusively the Sam Ash fuzz box and also the Jordan boss tone. And then to round out and to finish off the 1960s, we had the Electro-Harmonix Big Muff and the Big Muff Pi. So all in all, that was 62 different fuzz circuits, and they all fit into 8 topologies. Now, if we look at the evolution of all those different circuits and those 8 topologies, that's where things start to look even more interesting. Now, at the beginning of the 1960s, actually in the decade before, in the 1950s, guitarists and musicians were already working with distorted guitar tones. And a lot of that was found by accident. Either the amplifier was damaged and holes got put into the speaker, or they were intentionally put in there by jabbing the speaker with a pencil or slashing it with a knife or something like that. Take a listen to Link Wray's Rumble from 1958 to get an idea. By the way, I should mention that I'm having a separate playlist of the songs that I'm going to mention in this video because there's been so many copyright issues like Davey 504 and The Sound of Silence. It's easier for me just to say, look, here's the video over there. I'm going to have that playlist, and you can reference that stuff in another window or just at another time. Anyway, so by the time Marty Robbins came out with his song Don't Worry in 1961, innovative guitarists and electronics tinkerers like Lee Hazelwood and Orville Red Rhodes had already developed their own distortion or fuzz circuits. Now, sadly, neither example of a Lee Hazelwood fuzzbox or a Red Rhodes fuzzbox exists as far as we know. But anyway, moving on. You can hear an example of the Lee Hazelwood fuzzbox from the 1960 recording of Sanford Clarke's Go On Home. You can also hear an example of Red Rhodes fuzzbox in the Ventures 2000 Pound B Part 1 and 2. There's a whole interesting story about Red's fuzzbox that I'm going to get into in another video just about that fuzz circuit. Patented in 1962 by Glenn Snoddy and Revis Hobbs, the Maestro Fuzztone FZ-1 was meant to recreate the glitchy equipment that was used to record Grady Martin's baritone guitar solo in Marty Robbins' Don't Worry. The Maestro Fuzztone is a 3-transistor saturation cascade. Introduced in 1962 with the Maestro Fuzztone FZ-1, this is the circuit that launched the fuzz phenomenon. Most famous in the Rolling Stones' I Can't Get No Satisfaction, which came out several years later. The topology is a series of 3 cascaded common emitter transistor stages. How it works, the topology is heavily misbiased on purpose in this second stage. The first transistor acts as a buffer with a high input impedance. The second transistor is intentionally biased low so that it shuts off for part of the input signal. and it causes asymmetrical clipping. And the third transistor, possibly exceeding the capabilities of the power rail, drives the output signal. The sonic character is bright, buzzy, and highly gated. It sounds like bees in a can with a raspy tone that dies off pretty quickly. Next up is the Shunt-Series voltage feedback, or the two-transistor English Fuzz Face topology, is arguably the most famous and dynamically responsive topology that was perfected by Dallas Arbiter. The original circuit was actually developed by Dick Denny, who was an engineer at Vox, and he prototyped the early two-transistor fuzz or distortion circuit in England back around 1962, and that design was later put into the Vox V816 distortion booster. The topology known as the two-transistor English Fuzz is a shunt-series feedback voltage amplifier. Now, what does that mean? Okay, so instead of just sending the signal straightforward, a resistor loops the output signal from the emitter of this second transistor back to the base of the first transistor. The fuzz potentiometer alters the gain of the second stage and also the amount of feedback that is going back to the first stage. The sonic character is highly interactive because the input impedance is incredibly low, and it interacts directly with the guitar's pickups. Rolling back the guitar volume knob completely cleans up the distortion into this nice glassy tone. The best example I can give you of the Fuzz Face is listening to the opening sequence in Jimi Hendrix's Foxy Lady. You can hear how the character of the guitar tone and the distortion changes as he rolls up the volume on that opening note. The next topology is an evolution of the Fuzz Face topology. This is the three-transistor modified Darlington, or the Sola Sound Tonebender topology. Developed by Sola Sound for the Tonebender Mark II in 1966, this topology was famously used by Jimmy Page, most notably in Led Zeppelin II. The design takes the two-transistor feedback topology described in the Fuzz Face topology and inserts a high-gain common emitter transistor preamp stage right at the front input. So the first transistor acts as an isolator and a massive boost. It fixes the low input impedance issue with the Fuzz Face, and it hits the subsequent feedback loop extra hard with this wall of signal. So the sonic character is you get a whole lot of sustain and rich compression and some aggressive saturation. It doesn't clean up like the Fuzz Face does when you roll back the volume on the guitar. As a good example of the Tonebender topology, I would listen to Led Zeppelin's Communication Breakdown in those first few aggressive opening chords. In the middle of the 1960s, we move away from the cascaded gain and transistor slamming to get the fuzz signal, and we move on to a set of topologies which focus on phase manipulation, like the Roger Mayer Octavia. And this uses a differential pair and frequency doubling to get a much more interesting sound. Introduced in 1967, with the Univox Super Fuzz and the Fender Blender, this layout is aimed to create a completely tracking octave up fuzz effect. The topology uses this phase splitter transistor stage to divide the audio into two identical signals that are 180 degrees out of phase. How it works is that these inverted signals are pushed through a rectification circuit, a pair of tightly matched diodes or transistors even in some cases, and by flipping the negative half of the audio wave upward, the fundamental frequency is also doubled. The resulting sound is metallic and clangy with ring modulator kind of tones, producing this distinct and ghostly upper octave note that you can hear when you're playing. Best example I can think of for an octave fuzz is another Jimi Hendrix tune, Fire. A slightly different technique in phase manipulation. This is parallel phase blending, or the Maestro Fuzzrite topology. Released in 1966 and attributed to Ed Sanner of Fuzzrite, this design represents a highly unique approach to waveform shaping. Instead of just smashing the signal forward, as we've done before, this manipulates phase cancellation. Okay, how it works. The input signal hits this first booster stage, and then the signal is split. One path takes this slightly overdriven and now slightly out of phase signal and runs it through a second booster stage where it's inverted again, and the phase is slightly more off, and the signal from both of these branches are sent to this blending pot, and depending on how this is set, you get phase cancellation. At specific blend spots, the overlapping frequencies destructively interfere, and it carves out the fundamental frequency and emphasizes these higher order harmonics, and it gives the Fuzzrite its famous buzzy signature sound. Best example again is going to be listening to the Venture's 2,000 pound B, although there is some disagreement on whether they're using the original Red Rhodes fuzz box or they're using the Fuzzrite Fuzzrite circuit, which was actually put into a prototype amp used by Nuki Edwards. We might actually be hearing both of those fuzzes. I'm still researching that right now. After the phase manipulation topologies, we get into diode hard clipping circuits, starting off with the cascaded boost clip buffer, or SAM-Ash fuzzbox topology. Introduced in 1967, this topology is historic because it decoupled the distortion generation from the output volume and tone shaping. This is a technique that's used in almost every modern overdrive and distortion pedal today. The topology uses a linear three-stage network consisting of a voltage gain stage, a passive clipping network, and then followed by a current buffer stage. How it works is the first transistor is a common emitter amplifier, providing a whole lot of voltage gain into the second stage, which is a pair of diodes meant to shunt the signal directly to ground, slicing off the top and the bottom of the audio wave, and this produces hard clipping. This is followed by an emitter follower. This stage doesn't provide any voltage gain, but it is a high output impedance, and you get plenty of current gain coming out of here. What does that mean in guitar terms? It's not a tone suck. And the output buffer ensures that whatever amplifier or pedal that you plug this thing into next, it won't alter the behavior or the frequency response. The best example I can think of this sound is the early Leslie West recordings, most notably Mississippi Queen. Leslie West was also known to use two of these fuzz pedals back to back for some extra harmonic distortion. Next up in our diode clipping, we have the capacitive coupled Dual-NPN Cascade, or the Jordan Boston California circuit topology. Introduced in 1967 or so, the architecture is a linear cascade of two independent, capacitively coupled NPN common emitter voltage amplifiers, directly terminating in a passive shunt diode clipping network. Our first transistor is a high-gain NPN stage that boosts any weak input signal. Our coupling capacitor here blocks any of the DC voltage and only passes the AC voltage to the second stage. And depending on how this stage is biased, this can be driven into some asymmetrical clipping, and that's followed by the two-diode clipping stage, providing some hard clipping and shunting excess voltage to ground. The result is, because the stages are decoupled by capacitors, and it removes any kind of interactive sag like we had in the Fuzz Face. The attack is razor sharp and immediate, and it can be extremely aggressive. A great example of the Jordan Boss Tone California circuit is Norman Greenbaum's Spirit in the Sky. Coming to the end of the 60s, we have the multi-stage shunt feedback diode clipper, or the Big Muff Pi topology. Designed by Bob Meyer and Mike Matthews, this 4-transistor layout completely breaks away from the previous designs in the 1960s by daisy-chaining independent self-biasing gain blocks with local feedback loops. Now, these two middle sections resemble a logarithmic amplifier. Each common emitter transistor has a resistor linking the collector back to the base for a stable bias. In series with a coupling capacitor, these two back-to-back diodes are placed in parallel with the feedback loop. I've omitted them from the drawing here, but the mechanism is such when the signal voltage is low, the diodes are in an off stage or in an off state, creating a high resistance. That puts these transistors into a high gain mode. As the signal level increases, the diodes become forward biased, resulting in a low resistive state and effectively turning down the gain of that transistor stage. All right, going through step by step, the first transistor is an input booster, pre-amplifying any kind of weak guitar signal coming in here, and gives us a fairly uniform level before sending it through to the next stage. Stages 2 and 3 are our log clipping stages. The signal passes through the first diode feedback loop, squaring off the waves and creating a form of soft clipping. It immediately hits a second log clipper stage, compressing it even further, and then we come into this tone stack. The tone stack is passive and has an interactive high pass and low pass filter. The mid-range frequencies are around 1 kilohertz, and it gives the Big Muff this iconic wall of sound with plenty of low end or very piercing highs. Stage 4 is a recovery boost gain stage. Because the passive tone stack takes a lot of the signal out of the volume, this transistor stage cleanly boosts the signal back up to a line level. Now, while traditional 1960s hard clipping topologies like the Sam Ash or the Boss Tone threw away voltage by clipping the signals directly to ground, the Big Muff's pseudo-logarithmic feedback loops here compress the waveform within the amplifier stage itself. It creates this incredibly smooth, compressed kind of distortion and sounds less raspy like other 60s fuzzes, and has a more singing 900-pound violin kind of tone. Do I have an example? A great example of the Big Muff Pi can be found in some early Santana recordings, most notably Black Magic Woman. So there you have it, 8 different topologies of 1960s fuzz circuits. Now, in terms of being a mad scientist, sometimes being a scientist is some of the boring stuff, collecting a bunch of data, categorizing things, and searching for patterns that emerge from that. It's not exciting, at least not for everybody, it's not. But there is value in doing this kind of stuff, especially for research. Now, one thing that I am surprised about, I was trying to find the fuzz for a very specific song, and it seemed to be hard to reproduce, Spirit in the Sky, as played by Norman Greenbaum in 1969. After looking at all of that data, I came across 2 names that I wasn't expecting, and that's Lee Hazelwood and Red Rhodes, some of the early pioneers in fuzz pedals and fuzz circuits. Now, even though we don't have examples of their circuits, that we can directly take a look at, they were never turned into commercial products. But we do have the recordings, some of which are on the playlist. and we can try to, look at those recordings as forensic evidence of what that circuit might be. And I'm still working on a follow-up video on red roads. There's 3 different possible circuits that I think could be his. And it's kind of surprising. Some of them are in this list and part of the topologies, but I'm not able to quite put my finger on it yet. Anyway, that's for a future video. I hope you found this kind of stuff interesting. Let me know your thoughts in the comments below. I know some people were looking forward to a dedicated video on topologies, and I'd like to have your feedback. If you didn't like it, you're probably not listening to this ending of the video. But still, if you didn't like it, if you have some criticisms, throw them my way. I'm too old to, have the luxury of feelings. So anyway, let me know your thoughts, and I will check you guys in the next video. I don't know what it is yet, but catch you there.